Hello everyone, my name is Ransom Allphin, and today we'll be talking about electromagnetic waves. First thing I'll be discussing today is the famous physicist James Clerk Maxwell. He lived in the 19th century and was instrumental in establishing the electromagnetic theory. He brought together the work of many other physicists like Ørsted, Coulomb, Gauss, and Faraday to come up with equations that make up the electromagnetic theory. Now, I'm not smart enough to fully understand and interpret these fancy equations, but I know that they help to encompass the major laws of electricity and magnetism. You can see on the right there are these four laws that were made by these different physicists, and he took these equations and tried to understand them as a whole rather than as separate pieces. He found the relationship between electric and magnetic field lines and how magnetic field, and if you change that, it creates an electric field, and vice versa with a magnetic field is created by moving electric fields. So he took this knowledge and understanding to create this equation you see at the bottom of the screen to find the speed of light and of an electromagnetic wave. So at the time, these waves were merely his prediction. He didn't really have any proof behind these equations, but later on it was verified experimentally. But this equation he found for the speed of light is still used today and is the value that we even use for the speed of light. So how he calculated this is he used two constants, the permittivity and the permeability of free space, and basically those are just the capability of an electric and magnetic field to permeate a vacuum. So these two constants were put like 1 over the square root of these two constants multiplied each other equals c, or 3 times 10 to the 8th meters per second, which is the speed of light. So next we'll take a look at how these waves come to be, or how they're created. So there are two parts of the wave, and the first part is the electric field. It also can be created with changing a magnetic field, but in this example we're talking about an alternating current, so an electric field that's being changed. So as this alternating current goes up and down this wire, you see that an electric field is created opposite of the positive charge. And as the alternating current changes and the positive goes to the top, the electric field goes to the bottom, creating this wave-like pattern. And it goes away from the alternating current at the speed of light. So this is just half of the story, because the magnetic wave is created perpendicular because of the current in the wire. And these two waves come together to create a transverse wave, like the one shown in this cool animation. So there's an interesting relationship that was found between the two field strengths in a wave that is expressed by the equation E over B equals C. E being the electric field strength, and B being the magnetic field strength, and C being the speed of light. So as you see, the greater the electric field strength, the greater also the magnetic field strength must be. So you can also use this equation in the idea that a wave's energy is proportional to its amplitude to postulate multiple equations for intensity. You can kind of substitute the variables in order to find different ways to calculate the intensity of a wave. Now, if you understand this, you understand what exactly a wave is, you're able to use this knowledge to apply it to our lives. And many people have done this with the use of TV and radio signals, X-rays, microwaves, and even just visible light are all examples of electromagnetic waves in our lives that we see every single day. I'm not going to go into the details and technicalities of how that actually works, but it's important to note that these things aren't just something you learn in chemistry or physics class. It's something you see every day in your life. There's also a little joke for you guys to really lighten the mood. You know what I'm saying? So we're gonna quickly look at a practice problem I got from the book, actually. So it's pretty simple, but it says here on its highest setting, a certain microwave oven projects 1 kilowatt of microwaves onto a 30 by 40 centimeter area. So part A is asking what is the intensity in watts per meter squared. Part B is asking to calculate the peak electric field strength E in these waves, and C is asking what is the peak magnetic field strength B. So we can use for the first part our understanding of what intensity is, which is power over an area, and just use what we have here, our units, 1 kilowatt over 0.3 and 0.4 meters, and you get an intensity of 8.33 times 10 to the third watts per meter squared. So it also has a note here that peak intensity is twice the average. So you can just take that average and multiply it times 2 and get the peak intensity. So for part B, we're using those equations that we saw on the slides earlier. We can just rearrange it, and this how it shows there. Plug in the values that we found in part A for intensity average, and if we calculate that out, we'll find the electric field strength to be 2.51 times 10 to the third volts per meter. And we can also use that simple equation instead of using the more complicated intensity equation to find the magnetic field strength, and just divide that by the speed of light, and you will get 8.35 times 10 to the negative 6. And so that's all I have for you guys today. Thanks for listening. I got all my information from OpenStack's physics textbook. It was a good time. Thank you very much. Stay safe out there.